So we talked about all of these different concepts in the sense that we've been exposed to all of them. So today I'm going to do one full lecture, one full lesson on radical expressions, how to simplify them, how to recognize them, how to use them, and how to put them into your calculator, which will be really, really helpful. So we're going to start with square roots and move to nth roots and then talk about simplifying radical expressions. And then we're going to talk about using rational exponents to simplify radical expressions. They're all tied into the same thing, so we should be able to get through this hopefully in the next few minutes. All right, so let's look at square roots first. Squares are defined, squares are defined by the idea that if you multiply two numbers and they're the same number, they create a square. So for example, 2 times 2 is 2 squared, right? The same is true if you use a variable. A times A is A squared, okay? So A times A is A squared. So what happens when we want to take a root is that the root is defined as finding the number that you multiplied by itself. That's not a technical definition, but that's a definition we're going to use, okay? Finding the number that's been multiplied by itself. Okay, so for example, in this particular case, we have 2 and we have 2, right? We know that 2 squared is 4. So if I ask you to take a square root of 4, okay, we use that radical sign. What I'm looking for you to do is find what number, when multiplied by itself, equals 4, right? Find the number when multiplied by itself equals 4. And so we can see, of course, from up here that it's 2, and so this becomes 2. Now there is the whole plus or minus question, but we're not going to get into that right at this moment. So the definition of square roots is to find the number that when it's multiplied by itself gives you the value under the radical sign, right? And that's what we call this particular sign here. You'll hear me use that term a bunch. It's called a radical, okay? And I use that term a lot because that tells us a lot of things about the operation. The radical sign, though, is an operation. The radical sign does not mean multiply, does not mean divide. It is an operation in and of itself. Okay, it is an operation in and of itself. So the next thing we're going to look at is roots other than square roots. Okay, so we call those nth roots, right? Roots that have something other than a square. Okay, and anything can be a root. Okay, you can have a third root or a fourth root. And essentially what you're doing is always the same thing. An nth root looks for some number multiplied by itself n number of times to get some value. So for example, let's use 16. Okay, if I have 16, I can factor 16, prime factorization, right? Becomes 2 times 2 times 2, 2, 4, 8, 16. Okay, so here's the thing. I now have some information about the number 16. I can now ask you to take the fourth root. Okay, so this number outside the radical sign, remember this part, let's do this. This part is called the radical. Okay, this part on the inside tells you to what root, okay, to what root. And it tells you that by asking you or telling you to find the number when it's multiplied by itself, that number of times equals the number under that square root sign. So what this is essentially asking me is something times itself 4 times equals 16, okay? And so what happens is then we can look up here, because I derived it the other way, and we can say, oh, 2 times itself 4 times is 16. Okay, so this is the same thing. There's 4 of them here, right? I've got 4 here. And so when I'm trying to find the fourth root, I'm looking for groups of 4 of the same number, right? This group of 4 2's should match the number outside that radical sign. So then this ends up being 2. So what happens then if you have something that's not quite so obvious, right? What happens if you have something that's not quite so obvious? So let me give you a different one. 27x cubed y to the 6th. I kind of just upped the solution game here a little bit. I'm going to take the cube root of that. So what I'm looking for here is groups of 3, right? This number out here tells me that I want to find groups of 3. So let's prime factorizate prime factor this particular term. Okay, so 27 is 3 times 3 times 3. X cubed is x times x times x. I'm totally going to run out of room. And then y to the 6th is y times y times y times y times y times y. Okay, there's 6 of them. And then this whole expression, I know I ran out of space on that line, is taken to the 3rd root. Okay, this is taken to the 3rd root. So I'm going to pick a different color here because I've used up a bunch of them. All right. So what I'm looking for here is groups of 3, right? So I can find a number of those. Here's 3 3s. I see 3 x's. And I actually see 2 groups of 3 y's, right? I actually see 2 groups of 3 y's. So then what I want to do with that is, for every term that does have a group of 3, I can take that factor out of that radical sign because I've rooted it and use it. So if I have 3 3's, then once I take it out of that cube root radical sign, it becomes 3. And if I have 3 x's and I take it out of the radical sign, it becomes x. And then here's the tricky part. I have 2 groups of 3 y's. Well, each y that comes out of that radical sign becomes y. But if there's 2 of them, then I have 2 sets of them, which is y times y, which becomes y squared. Okay? So this particular root here becomes 3xy squared. So what you're looking for is taking out groups that match, okay, that root sign. Okay? The next couple of things I'm going to do, I'm going to combine a couple of things that we've done. We're going to continue to find nth roots, but I want you to be able to write them using rational exponents. So there's a couple of different types of rational exponents I want you to think about. Okay? There's this one, which is that x to the power of some rational number, okay, where a cannot equal 0. Remember, we can't divide by 0, but where a can't equal 0, this takes it from x, this 1 in the numerator, okay, this 1 in the numerator that you see, it becomes the power, okay, and then this a in the denominator that you see there becomes the number of the root. Okay, so what happens here is that it becomes the root, and that a goes outside that radical sign. Okay, so for example, let's look at one. Let's undo that. Let's look at a perfect square because that makes life easier, and let's use 81. 81 to the power of a half. Okay, so if I use 81 to the power of a half, 81 is my x. It's to the first power. I'm going to take its square root. We know that the square root of 81 is 9. Okay. There is also another way to think about this. A lot of calculators do not have a root that goes beyond a square root sign, right? When you start looking for a cube root, or a 4th root, or an 8th root, calculators don't like to do that, okay? So what you can do is that if you can translate the root into a rational exponent, you can put anything you want into a calculator because a calculator knows how to do fractions, right? So let's look at one that generalizes for things that have more than 1 in the numerator, okay? So we're going to do it this way. X to the power of b over a is equal to, again, this numerator in the top is going to be the power. And then this denominator in the bottom is going to be the root. Oops, I didn't mean to do that. I meant to do that in blue. Okay. So this is how it looks. Okay, so let's say that I am asking you to take a different number to a root. Okay, I'm asking you to take a different number to a root. So let's use one that I know will work out nice and clean. Okay, let's take 9, and let's take it to the power of 2/3. What a weird thing to do. Right? Now, typically, if you ask, actually that's not what I went to do. Let's do it the other way. But now you're going to know the answer. Let's take 9 squared, and let's take it to the 3rd root. Okay? So typically on your calculator, this is something that's very difficult to put in there, right? I know that 9 squared is 81, but I don't know how much that'll help, right? And I'm still trying to do this cube root, and my calculator might not do a cube root, and what a pain. So what do I want to do? I want to rewrite it as a rational exponent. And so I can rewrite this as 81 to the power of 1/3, or if I wanted to, okay, if I wanted to, I could use this value and this value, the 2 and the 3, and just write an expression for an exponent using that. I could have written this as 9 to the power of 2/3. Now, let me warn you, on your calculator, you must put parentheses around the 2/3. Why? Because the order of operations dictate for your calculator, right? Your calculator knows order of operations. It never messes them up, okay? Your calculator knows that it needs to take the exponent first. So if you don't divide inside of parentheses, which is what's supposed to be done first, right, before you do your exponents, if you don't divide first, it'll take the whole thing and it'll square it, and then it'll divide the whole thing by 3, which will not give you the correct answer, right? And so let me show you what I'm talking about here. Let me find my calculator. Oh. Let's see. Where's my calculator? All right, so let's use this scientific calculator here and use the same problem to do it. Okay, so all of you guys have a scientific calculator. Most of you guys have a graphing one. So it'll look more or less something like this. If I take 9 and I take it to the power of 2 divided by 3, so I'm going to use my x to the power of here, right? And I do this, it's going to tell me that the answer is 27, okay? Because what did it do? It squared it, made it 81, then divided it by 3. But if I clear that, and I take 9, and I take it to the power of 2 divided by 3 inside that parentheses mark, right, and I hit equals, I get a completely different answer, okay, because your calculator knows order of operations, all right? So what does this have to do with then simplifying radical expressions? Radicals can be treated like variables almost, okay? So when you're doing radical expressions and trying to simplify them, you can do it almost like you would another variable. So let's do, for example, times the square root of 5. So if I have 2 times the square root of 5, and I add it to 3 times the square root of 5, what's really interesting here is that this square root of 5 and this square root of 5 are the same square root of 5. So I can almost treat it like a variable, and this can then equal 5 times the square root of 5 if all I do is add up these values, okay? The same is true for subtracting, okay? So when you're reducing or you're simplifying radical expressions, this is a really good way to do it, right? To be able to combine them as much as possible. All right, so for example, let's do one that it's not quite this clear, okay? Let's do 4 times the square root of 50 plus 3 times the square root of 2. Okay? So this doesn't look like you would be able to do much with it. Okay? So we're going to kill 2 birds with 1 stone here. We're going to simplify the first radical. Okay? So let's simplify the first radical by looking at this 50. I'm going to write it over here so we can see it. And 50, when I'm simplifying, remember, I'm always looking for groups of perfect squares. So 50 comes from 25 times 2. 25, Glory, is a perfect square. Okay? So if 25 times 2 is 50, then I can rewrite this expression as 4 times the square root of 25 times 2 plus, put my equal sign there, 3 times the square root of 2. Now, I know now that this 25 is a perfect square. Okay? So once I take the square root, I'm going to multiply it times the number that's outside the radical, so it's going to end up becoming 4 times 5 times the square root of 2 plus 3 times the square root of 2. Okay? This 4 times 5 here becomes 20 times the square root of 2 plus 3 times the square root of 2. Okay? And so what ends up happening then is it becomes 23 times the square root of 2. All right? So hopefully so far this has been helpful. Let's do one more thing, okay, before we move on outside of radicals, and that is simplifying radical expressions. Okay? Simplifying radical expressions. And so I'm actually going to type this up for you so that you can have it, something other than my handwriting. Okay? When we simplify radical expressions, what we're looking for are some specific things. All right? So this is the definition of a simplified radical. And you do need to know this, right? These are things, when I say simplify, I expect these conditions to be fulfilled. Okay? There are no negative exponents. There are no positive exponents, or there are no exponents that are positive integers in the denominator. Okay? There is no complex fraction. And when we talk about complex fraction, what that means is really a root sign in the denominator. They call that a complex fraction. Okay? And the number that's inside, they call that the index. The number inside the radical is the most simplified or the least possible number. Okay, so, all right, so what do I mean by all that? Let me show you. All right, let's simplify some expressions here. Okay, so let's look at, let's do one that's a little bit more complicated just so we can do it all at once. Let's do 1 over 5 plus the square root of 2. Okay, remember we've learned before that we can simplify denominator by multiplying by its conjugate. So we're going to take care of a bunch of things at one time. We're going to take care of the complex fraction problem. We're going to check to see if the number inside the radical is the least possible number, and we're going to deal with the other two as well, but those are kind of already built in. So let's do this one. Okay, remember my complex, or not my complex conjugate, my conjugate, complex conjugates have I, right, is the other half of the a plus b times a minus b equation. So it becomes, in this case, 5 minus the square root of 2, right? Remember that this here gives me my a squared minus b squared term. The top is going to remain the same. And the bottom then gives me the a squared minus b squared term. So a squared is 25, b squared is 2. So that gives me a denominator of 23. That's nice and convenient. And so this is a simplified radical. Okay? There are no negative exponents. There are no exponents that are positive integers in the denominator. Obviously, the power of 1 doesn't count. Okay? There are no complex fractions. That was really what we've dealt most of with a root in the denominator. And the number inside the radical is the least possible number. So it's the square root of 2. It's not the square root of, for example, 24, where you can factor out of 4, right? So we did that earlier when we simplified roots. So when you're asked to simplify radicals, this is what I expect you to do. So this should give you enough information now to solve a variety of different problems that we've been working on, and then we can work on some of these in class over the next